Alright, another draft physics video presentation. Yes, kind of a tired edition, but whatever, we'll endeavor to persevere. Anyway, comments. They do wear you down. And then scatter, I think, is going to be the theme of the video, sort of. Everything is scatter. In a sense that everything that turns into some kind of coherent or shaped energy likely got there through the process of scattering through a matrix of objects, electrons and protons, that neutralized or normalized the scatter irregularities into something more regular. So there's a lot of ways to analogize this tension on a spring and oscillators and all that stuff, but it doesn't really have anything to do with wave mechanics. It just, you really can understand it as just being energy balancing over an object, like even the way heat travels through something, and it all becomes one temperature, even though it started off with one bit being really hot. That kind of thing. And it's because the heat is essentially scattering through the object. Anyway, so that's sort of underlying theme thingy, and we'll end up talking about whatever, the expansion of the universe and redshift and how it's, why isn't scatter a good answer? Anyway, I'll get to that. Alright, no point. I guess there's some language difficulties, international, doing this whole world communication thing. I guess that's what I'll blame, because I can't understand much of this. Anyway, happy to hear an acceptable scholar is willing to non-mathematically answer. A huge amount of question you got for them. Yeah, I'm always baffled that they do not ask you. I don't know what that means. You're surprised they don't ask me. You're surprised the physicists don't come to me for physics answers. Oh. Don't get me wrong, some point you bring. Question mark. BOF. I don't know. Big awful fucker. Anyway, awful. Awful. But a huge amount of question you pose, question mark. I don't know. There are very interesting. Those are very interesting. Well, at least that's one sentence I can understand. Yes, the subject is interesting. Physics is interesting. You might want to pose those questions offline. For what purpose? So he can manufacture answers. Some of that's going to happen inevitably. I mean, I'm only paying him for the, live performance stuff. So he is apparently doing some preparation, that's almost against the point. The point is to bring up the fact that physicists are trained, and their focus is so much on math and using math to formalize a model of math. And actually this particular physicist is kind of cynical about the power of mathematics, but anyway, they don't really do the actual look at the experiment. They just listen to the teacher tell them that something's the truth, and then they say, okay, that's the truth. Light is electromagnetic, blah, 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 because Maxwell said so, and therefore that's what it is, and they never think outside of that box. And that's the thing to sort of bring up, is that the box was never really established as the right box. You all just applauded, and everybody said great performance, but, a real critic, wasn't involved in that decision. You all just went along. But anyway, like a list of question, etc. or however you both want to do this. I'm sure, I sure hope you stay calm. Yeah, well, the point will be is, yeah, that's a kind of a good thing to do. Yeah, I sort of understand that. Finding someone willing to even consider questioning established. Yes, it's whatever, question mark. Yeah, it's not that, you know, there's not too many, I mean, but scientists really should. This is one of the whole things of science, is that they just kind of want to test your theory. You kind of want it rigorously tested. You don't want it to have holes in it and be fake and phony. And that's sort of the sad fact, is that a lot of physicists just want to build on what they've already know. They don't want to test what they know, because that's not as much fun. It's building the new unicorn. Finding somebody willing to consider, okay, the list is very short. Yeah, well, one of the things in this whole conversation is, you know, just little bits of back and forth I've had with the guy so far, and he has this kind of understanding that all the physicists out there are just looking for an opportunity to prove something wrong. And, you know, because Nobel Prizes are won that way and all that kind of stuff. I'd say it's the opposite is so glaringly true. You know, I bring up the fact that they've never even redone the Eddington experiment with all the technology we have now. Just no use of modern technology to redo the experiment. I mean, those kind of glaring things. And like the double slit, there's been no real serious hard analysis of even what the idea of a single photon is. You know, testing the idea of sending light in small amounts, and what that exactly involves and how you even test for that. But anyway, I mean, it's just been so little scrutiny, and then, like I said, some of this stuff doesn't take any real hard money. The radar experiments and the slit experiments, you know, are really cheap. Just takes a little bit of precision, you know, having devices that can measure small voltages and all this kind of stuff. I would start with double slit. It's a trap. I don't know whether you meant I wouldn't. I don't know. But whatever. That's where we're going to probably start. So, but whatever. You know. Yeah. So sorry. Write better, please. Yeah. That's all I can say. Hi. First off, I'm not a scientist. Let's get that out of the way. My question is about light and darkness. I live in a place. See, these kind of questions are okay. I mean, you can tell me something like, well, I have a hard time getting my shoes on. Did science invent any objects that make it easier to slide your foot into a shoe? You know, I could answer some questions like that, but I mean, I don't know. You know, anybody can answer some of these questions. You don't have to ask me. Anyway, about light and darkness. I live in a place the city lights doesn't have an effect on the night sky. I live in a place where city lights doesn't have an effect. Well, you can't really say that, because even though you think you're far enough away, you're really not far enough away. I mean, you know, I'm 40 miles from New York City, but New York City is, you know, lighting my sky whether I like it or not. Anyway, in clear night skies, everything is pitch black. Man, well, it really shouldn't be pitch black. Something's wrong. Maybe there's, you know, some sort of electric company nearby or something, and there's, I don't know. Well, anyway. But it is cloudy or rainy outside. In the middle of the night, you can somewhat navigate outside, and the sky seems brighter for some reason. Yeah, well, it's reflections, you know, scatter again. Does clouds have some kind of light source? Well, that would be kind of the wrong way to think. So you probably should figure out that one doesn't really work on your own. I mean, I shouldn't have to tell you that clouds aren't light bulbs. I swear when it's cloudy it seems brighter than it is just normal clear sky. Yeah, well, there's two things that can happen, right? If you live in a northern climate, the fact is just the way the earth tilts and everything else, the clouds can still be getting hit by a little bit of sunlight, you know, because of the angle. the clouds are way up there. You know, they can be pretty high, and well, they can be, and so they can still see the sun sometimes. Little, not the sun itself, maybe the corona of the sun, whatever. They get some sunlight ends up bouncing off bits of the atmosphere, and it can get to the clouds, and then it bounces off the clouds overhead, and that light ends up hitting you. The light mostly scatters inside of the cloud, so it's another one of those things where the light goes in and it bangs off of a lot of stuff before it finally hits you, so it gets diffused. So diffusion usually just means that you've taken something that would have been a straight line and you made a very unstraight line, so now it's where it pops out, who knows. So in a way it's like diffraction. Diffusion, diffraction, very similar concepts. And it's all kind of dependent on this scatter thing. So yeah, there's light coming from some city on the ground or something on the ground, and it's reflecting off the clouds. That's one of the obvious answers. The lights you left on in your house when you went outside, you know, made a small little contribution. You know, there's reflections from all kinds of places. And so yes, the clouds end up reflecting light back from the surface is probably the cause. But it's also possible that the cause is the clouds are high enough that they're catching a little extra sunlight, even though it's dark. It's night where you are, where the clouds are, it ain't so dark. And so you're getting some scattered light back from them and such. Yeah, I think it's a good enough answer. That would be my answer. I don't think physics is going to give you a much different answer. I'm fascinated by this topic. Good. But as a beginner, I still get pretty confused by some of the language. I find myself having to constantly stop and look up words I haven't heard before but never truly understood, like polarization. Yeah, well... and transverse. Well, I don't use transverse too often, so it's really not a problem. I mean, I think it's silly enough to do this wave thing. I think it's really silly to have it waving both ways. So, yeah, it's a, kind of a silly concept. And phase. Well, phase is pretty simple, actually. Anyway, the concept I'm having the most trouble with is the difference between the meaning of the word wave and wavelength. No, that one should be really easy for you, frankly. I mean, ocean waves coming in, there's a distance between, you know, the hump and the hump, or the swells, you know, the bottom and the bottom, and the tops and the tops. There's a distance between them, and that's the wavelength, the length of one of the waves. And so, yeah, the wavelength is just counting the humps and saying how many humps are there and how far apart are, you know, where I counted, and you just... that's the wavelength. I mean, it's pretty simple. Those words seem to pop up most of the other definitions. Those words seem to pop up in most of the other definitions, and I feel like I'm just going in circles trying to understand the difference between something having a wavelength and something behaving like a wave. Something that has a wavelength, okay, is just saying anything with a frequency. So if I had bowling balls and I threw them down an alley precisely, you know, at a specific time, you could understand that there'd be a specific, you know, at the same speed, there'd be a specific distance between them. Now, that would be technically a wavelength. You could call that a wavelength between them. It's a distance between them. But in no way are the bowling balls acting like a wave. So the difference between something that you're going to call a wave, I would say, to be fair to the language and the words and the vocabulary at all, I could probably move that over. I thought it goes this way. Yeah, it should go that way. Anyway, you know, is to understand that waves are, generally speaking, a concept where you're taking stuff or a substance, and you can understand the substance as being stuff, you know, bits of stuff, but they are connected to each other. There's something tying them together. So the idea is that if something happens to one of them, it happens to all of them. So waves are kind of something that happens in what you'd call a medium, you know, a substance where, you know, so you could push on this one, right? And you just think of these as all being connected. You know, you push on one, okay, and that pushes on this one, and that pushes on this one, and that pushes on this one, and this one. They all move as you do that pushing. So that's the idea of where you can have something coming in this way, and it goes through a slit, for example. And the idea is that it would be, you know, it would have consequences because the stuff going along the surface would be slowed down, and so the stuff going here is going fast still, so you'd end up with a curve in the wave because the medium bends the pressure, it evens it out, and because these things all communicate with each other. But the idea is if we had just single little things, now they can look like they're waving, and then I could have individual soldiers and I could send them at a time, but they're not in any way connected to each other. So if I put them through something, they're just gonna, you know, the ones that can get through will get through, the ones that can't won't get through, and they'll just keep doing their thing. They won't bend or go crooked. Now the idea though is if I put barriers here, you know, on the surface that cause soldiers to get confused, that is, you spin them around and they don't know which way they're going, well then the soldiers on these edges would go all funky. You know, they could come out any one of these directions, and so they'd get scattered, okay, because they're having an interaction. So if it goes through the middle, it's okay, but if it hits these edges, then it gets into this rough spot and it gets confused which way's north and south, and it doesn't know where it's going, so it ends up going in some silly direction. But it's not waving anywhere. It's still at a frequency, so it still has a wavelength. See, frequency is just measuring the distance in time, where wavelength is measuring the distance in length. So the wavelength gives you the number of how many feet this is, okay, where frequency tells you how many of these things in a certain amount of time, seconds, you know. But they're the same thing. They're just different ways of looking at the same thing. One number goes up, okay, as you increase the the distance gets shorter, the frequency goes up. The distance gets shorter, the wavelength goes down. You get smaller numbers between them. So they're inversely related. And the fact that they use the two interchangeably, it does confuse things because one number is getting smaller with more, and the other energy is getting bigger with more, you know, so it's confusing. Anything else I need to say about that? No. I've decided there's nothing else I need to say about that. Oh, I should have said something about polarization. Well, anyway. So polarization just has to do with the fact that this thing, okay, this moving through space, you know, you're going in this direction, your wave, you know. And the idea would be is that if it was made out of particles and the particles had a spacing between them, they weren't perfectly in alignment, you can understand that as polarization. Now that's what I'm arguing polarization is. Now if you're to do it with a wave, it does get kind of more complicated to understand what a polarization is. So the idea would be that somehow you have this continuous energy, but that it has some limitation in the size. So, you know, where the traditional wave would keep going, polarization sort of means now there's a limit to how much wave there is. So there's only this much wave, and it has an orientation in space. That is, it can be in any one of these dimensions. It's traveling this way or this way. You know, it can be, you know, it can be in lots of different orientations. In terms of the straight line here, it could be, you know, it could be pointed in all these 360 directions if I was to move it around the board, or you can think of it this way, moving this way. But the point is it has a shape. So the thing is traveling through space, it sort of has a shape. You know, it has its frequency, its wavelength, its size this way, and then it has a size this way. That's the polarization. No. Close enough. You can almost see that. Almost. I don't have the other light on for some reason. All right. I don't think it might be superfluous to the point. Anyway. Alright, these seems to pop up in other definitions. I'm trying to understand the difference between something having a wavelength and something behaving like a wave. Okay. Any chance you are willing to briefly describe those seemingly rudimentary concepts in a way that my little monkey brain might finally understand? Yeah, well, it's not that challenging, actually. I mean, the wavelength thing, the frequency thing, these are kind of basic concepts, so if you're having a problem with that, some of these videos you're just not going to get. You know, I warn you that some of my questions would be painfully entry level. Yeah, it's not that I find it painful. It's just that you know, there's so many more stairs you have to go up. You know, that you have to get some of this stuff. You have to know what it is before you can talk about it. I think. I don't know. See, all of it is so broken by physics because they have used all this wave rhetoric for anything in a pattern. They're describing it as if it is in a medium, as if the little bits are physically connected and all this kind of stuff. And that only happens, their only connection to each other is actually the force, okay, interacting that they're in. So if they are jiggling, they're not jiggling because they have the ability to jiggle. Okay, and actual forces have to act on them for them to move. If they go this way because a force forces them. If they go that way, another force has to force them to do it. They can't do anything by themselves on their own. They're not. The physics doesn't allow for any of this self-motivating kind of idea. Nothing can be motivated from its closed system. It has to be motivated by an interaction with the world. Alright. Mark A. Thanks for the lucid, simple explanation. I hope it doesn't scare off your physicist. Yeah, this is a tricky question. This whole idea, just because I don't think he's going to, there's no way he can undo what I've done, in the sense that he's not going to be able to repair the old perspective in any way, because it's I've exposed the truth of it, the simplicity of what the double slit is doing, the four surface experiment, right? I mean, these really should be redefined as what they are. There's the two surface experiment, the single slit, and then there's the four surface experiment, the multi slit. It really is all about the surfaces and scatter. Alright, John, I'm back. Very interesting. I'm also wondering why the single slit diffraction. So you're just going to sit there and throw these words at me, even though the video itself basically is saying that's not what's happening. There's no magical diffraction. It's not a water wave. I mean, I went over the geometry. It's so simple, and you're not getting it at all. So this isn't about any mysterious Huygens principle or any of this nonsense. It's just about the simple principle that you have a surface, and the surface is what is mathematically relevant. These become 2-point sources. So the energy goes in, and what you're basically saying is yes, some of the energy just goes straight through and nothing happens. That's why this gets very bright. But, okay, most of the energy, or some percentage of the energy, some lesser percent, 20%, whatever it is, travels this path near the surface, and it gets, as I pointed out, it gets confused. It gets messed up, and it can leave this way, 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 right? And by going to all of those locations, there's just this simple mathematical truth that this distance from here to here is much longer than the distance from here to here. well, much longer. It's longer by the distance of this slit, this D. D spelled like a Q. D's go this way. This distance is the thing, and whatever wavelengths there are inside of there, however number of wavelengths of distance that is, that will be spread over this. You go from 0 to whatever, let's say 20, okay, 20 wavelengths. From this 9 degrees to this 0 degrees, you will dispense a difference in the two lines. The two lines will have a slightly different length difference at each location. The length difference is a maximum here and it's a minimum here. And that's all it's saying: in phase, out of phase, in phase, out of phase, in phase, out of phase, in phase, out of phase. So if there were two rulers, you know, very long rulers, that what longer we need, you could line the two rulers up here, and the 20 on one ruler would be lining up with the 10 on another ruler. And then when you got them to here, the two rulers would both be 10 at the same place and 10 at the same place. So they're 10 and 10 going this way. And then as you move the rulers, they line up, you know, the 18 lines up with the 19 on the other ruler, and then it's the whatever, you know, the number difference finally gets to 10, 20. So as you move the two rulers, there's places where the lines, the inch lines, would line up. Okay, they line up. You can see that. And then there'd be places where they don't line up. Okay, the inch lines are not lining up. And where they don't line up, no light because it's out of phase. Where they do line up, you get light because they're in phase. You don't need any Huygens crap. You don't need to make little wavelets and then try to make two waves and have them interfere with it. None of that crap is at all necessary. All you need to do is scatter the light, the pieces of the photon actually, right? The photon again, I don't have to keep explaining this to you, but I mean, it's made out of pieces, and the individual pieces get sent to different locations, and all you do is essentially break a photon and then remake a new one on the other side out of pieces that have the same phase, that are lined up on the right notches. That's it. Not complicated, not anything hard to figure out. And this works for the single slit, it works for the double slit, it works for the multi-slit. Just doesn't matter, because it's all it is about these surfaces and how far apart they are. And all you're measuring is each surface is a source, and then you're just saying how far away are the two farthest sources, and how far away are the next furthest sources, and how far away are the next. And you're just saying what's the maximum distance two sources are, and what's the minimum distance two sources are, and that'll tell you where they'll be in phase and out of phase. Now another point I wanted to raise, since I'm on the subject, okay. I mean, I was thinking about the, so we could do the double slit, I suppose, because it has both things in it. So there's this idea that when there's a single slit, I guess I'll have to draw the single slit just because I have to do the illustration. This middle bar is bigger, okay, than these other bars. It's twice the size, a little less than twice actually, turns out, when I did my measurement. So this one is like, you know, a little less than, right, less than 2x. So it's a little less than what two of these, the space two of these would take up. It's more like these two without this empty space between them. That's this distance here, this center one. And you can sort of understand that as being a consequence of, you know, these two lines would be the same length, and then these two lines, okay, would be a different length, but they'd all still be in phase. Okay, so this to this and this to this, they're a different length. You know, this is a very small distance, of course, and so they're so close to being the same that they're still close enough to being in phase that it makes one of these lobes this way. So one's going this way and one's going this way. So technically this middle is a 0 and these are both just 1s. You know, 1 is where all of a sudden you get to this edge, and that's where they're 2 out of phase. So they're going out of phase in 2 directions, right? So you have the alignment this way, and so going one way, you're going out of phase forward, okay, to that mark, and going the other way, you're going backwards. You know, so the marks are behind. You know what I'm saying? So the phase is from the right side is going one direction, the left side's going the other direction. So that's why there's 2 lobes that are combined, is because one is creating a maxima where they're close enough to be in phase. I guess I should have drawn that close. So there's the fact is that you don't have to be perfectly in phase to still be a visible photon. It can be, the line can be a little bit off here and a little bit off here, a little bit off there and a little bit off there, and it's still seen as the same as the right photon. So it doesn't have to be in perfect alignment. It can be a little bit off. So there's a little bit of flexibility, and that little bit of flexibility is what's making the size of these little lobes. And so the point is you have flexibility this way and flexibility this way, because you're shooting light in 2 different directions, so to speak. So that's why there's 2 lobes in the middle. Now, when you'd say with the double slit, why wouldn't you have the same circumstance? I mean, double slit still has the same idea. These 2 outside ones are still going to have the same scenario. They're still going to have a 0 here, and then there'll be a 1 and a 1. So why aren't they creating a bigger center? And the reason has to do with the fact that this envelope is what provides the background for the creation of the center. And what's the other point I wanted to raise? So yes, so it has to do with you're combining 4 sources. You know, when you're making light from these different places. So when you start to go to this other place, you got to consider there's 4 sources, and 2 can be in phase and 2 can be out of phase. These 2 could be in phase, these 2 could be out of phase. There's another reason I wanted to bring up, and I'm not thinking of it, so I'll take a quick pause. I think I'm back. Close enough, I think. So it really just has to do with a phase question, in the sense that you could understand that if this distance, okay, was you know, the distance of the slit versus the distance of this blockage thing, that if they weren't symmetrical, that means if they were they're out of phase, by the sense that this one's phase is not a whole number, this wavelength does not allow this wavelength to be a sub of it. So let's say this wavelength was creating blocks this size, and this wavelength, the outside slits, was creating a block size that was like 3/4 of that. There's a real problem in trying to line them up. Let's see, how is the best way to say that? So they'll be out of phase, and that's the wrong way to say it. I keep having it on the tip of my brain, and then it disintegrates on me. But it really just has to do with this distance. So if you make this distance the right distance, I would argue that this block actually does being twice as big. So if this is the right multiple of the phase of this interior one, then you will end up with a double. And when it's off of that, that's when they end up being single. Yeah. Well, I didn't explain that perfectly, but anyway, we'll move on, and I'll do that some other time. But it is there's a reason why something, it seems like it should, it doesn't, okay, for a reason, but it does it variably, in the sense that it's not that the centers are off. It's the wrong way to put it. Well, I will get back to that. Alright. You know, live performance, it's always got a glitch here and there. Alright, so where were we? Alright, single slit diffraction, Huygens principle. So again, I mean, the whole video I made was basically pointing out how Huygens is superfluous, it's silly, it doesn't make any sense, and I wouldn't use it, I wouldn't bother. I don't know why you're throwing it back in my face again. I've already dispensed with it. Wouldn't be a reason to explain the so-called interference. I guess you should say the so-called and then put interference in quotes, but anyway, in the dual slit experiment. So again, I'm pointing out it's not interference. You break photons and you remake photons. That's it. There's no interference anywhere. Therefore, removing the need to believe in superposition. Well, you don't need to believe in superposition to have some magical notion that you know, photons turn into wave functions. Superposition gets, you know, you have to take it a step further to come up with some notion of superposition playing a role. Anyway, I tried to find any articles that might target this, so I don't know exactly what you're trying to target. I mean, most rational physicists say they're both single slit, double slit is the same thing anyway. They're not saying one is a different thing. I mean, Professor Lewin explicitly says it. They're both caused by the same effect. You know, the same cause. But the ones I found get very complicated. Well, I don't know if complicated is a bad thing, but frankly, they all get convoluted is what they get. So I didn't link them. Need to look carefully to make sure they focus on it. Although if anyone can find some articles that might target this, I'd be interested. So again, I don't know why you're not convinced that you can understand it without any waves being involved at all. That the math, even their own math, is vector math. There's no waves in their math. They're doing the same geometry. They're just blaming it on something else. And they're trying to put it in places that doesn't work. So they're doing the same geometry by creating these stupid two waves, right? Which I'm arguing can't be two waves. If Huygens is applied, there should be two waves here and two waves here. So there should be four waves. But let's just take their silly the diagram of waves. The point is the waves end up creating these vectors of where there is constructive and destructive interference that are in the same places. Because of this, they're in the same places that I'm going to be putting them, because this is the length difference, you know, from this point to this point, and then this point to this point. It's the same length difference from this D, okay, ends up being the same as a derivative of this D. So you can't separate the fact that these D's are going to be related even if you create two waves as 2 point sources. But what I'm saying is, if you really want to do the math right, the math that really works, that really gets the right answer, is the math that recognizes that this is a distance and this is a distance, and that these two distances, D1 and D2, those two distances create the vectors that really work. Using the outside ones to create the little bars, using the inside ones to create the envelope. And that really works. So there's no waves necessary. These are just geometric locations where you just draw lines and you say, how long are the frickin' lines? And when I put this line against this line, how much is left over? How much is the extra here? And if it's a whole wavelength, can divide into that amount. If you can divide a whole wavelength in there with an even number, then you are on phase. And if you can't put a whole wavelength in that amount, then you're off phase. And that's all there is. Yes, so that's it for comments. All right, so we'll move on to something different. I don't know how different. All right, so scatter is what I wanted to get to. So we'll do a little scatter. So there's this thing called Compton scattering, and then there's this other one called Thompson or something, I don't know, whatever. But the idea is whether it's a large object, small object that you're hitting, and so the idea that photons travel, hit something, okay, so it could be an atom or it could be an electron. Now the idea of it hitting an atom is kind of nonsense, because we know the atom is an electron and protons, and it's not something you hit. It's not some round big ball that you just hit. So obviously scatter always just has to do with somehow hitting electrons with photons. Now the problem, as I pointed out, is photons are really big. Okay, now the bits inside the photon are very small, but the polarization of the photon is very big and the electron is very small. So there's no realistic hope that this thing, you know, with a big polarization with a P, and it's moving in this direction, this whole thing hits that one electron. That would be kind of nonsensical. Obviously the little bits hit the electron, and the point is that they scatter. So they could go this way, or they could go this way, or they could go this way. And the trick with Compton scattering is the idea that as they do the experiment on a number of, you know, there's a whole bunch of electrons or a whole bunch of atoms, that when the photon leaves, so photon goes in, photon comes out in some direction, and that there's a proportionality between the direction, that is how much off of where it was going, how much did it change in direction, and how much its frequency has changed. So if it had a frequency of this, the idea is that frequency is changed to something like this. It gets redder, okay, it red shifts. There's a loss of energy, so to speak, in time. So I would argue that what's really happening is little bits of the photon are hitting electrons. They're, you know, being changed in their direction. This takes time, so this bit has been slowed down in space, and that it's not progressing as fast. So it would have gone to this point if it didn't scatter. Because it scattered, it only got this far, and so you've changed its position, relative position, and by doing so, you know, you're consuming, you know, as each one hits at a different location. Okay, each one of those that ends up scattering that amount, okay, will be off by that same amount, and so they end up increasing the frequency, the distance between them. So they went in with a certain frequency, they leave with another frequency, and it's dependent on how much they're bent. Now, so, you know, that's sort of significant for the argument I want to make, because it, you know, but the point is any amount is going to create that. So if you just thought about the photon traveling, so I would argue, so that you have here, you have a way of explaining why there's redshift. Alright, so redshift is a fundamental premise for why they have to create this expanding universe and all this crap, because all the distant objects in space, their light is redshifted. Okay, we kind of know what color it should be, and it's not the right color. So the idea is that very far away objects, okay, the, you know, billions of light years, I don't know how to write billions of light years, very far away. So the light travels this very long distance, and I would argue that it's traveling through what we know, even when there's a complete vacuum. It's not a complete vacuum. There's still hydrogen atoms, and they're not very densely populated in space, but they're there. And when you're thinking of traveling billions of light years, an incredibly big, huge, gigantic distance, so the light will inevitably hit some of these little hydrogen atoms. It's really going to be hitting the electrons in the hydrogen atoms. It's going to be scattering a little bit, and it's only going to be scattering in this forward direction a little bit. So it scatters a little bit up this way, and then scatters this way, and it scatters this way, and scatters, you know, little tiny bits of scatter. And there's only a little tiniest bit of redshift when each thing happens, but you're talking about such an incredibly long distance that over that very long distance, these little bits of scatter ends up changing the frequency, right, from, you know, from this, okay, if that was your frequency, and it changes it slowly through all of those little scatters into something like this. So it red shifts it, just wearing the photon down in terms of little bits of lengthening in its frequency over a very long travel. So little bits of that are happening with each light year of distance it's traveling. So with each light year, you know, it might lose, you know, 30 nanometers, you know, of frequency, you know, something like that. Gain in wavelength, 30 nanometers or some kind of number like that, and that would be the cause of the redshift. And to me, it's a viable explanation. We know this Compton scattering causes this effect. Now, you know, and the little bits are doing it. So it wouldn't hurt direction overall, because each little bit is only being changed in its direction a little tiny subtle amount. So the photon is still maintained. It's such a great deal of distance, since it starts off with a very bright object, you know, with trillions and gazillions of photons, you know, and only one out of a, you know, trillion of the photons ever get to the target anyway. That you can sort of imagine them traveling this rather miraculous, you know, scatter path, and then a lot of them don't get here because they get scattered off in all kinds of directions, so they never make it. But some do, and there's some that do. It might seem like a miracle that it scattered and still stayed in pretty much a straight line, but something's going to be able to do that. When you send trillions, some of them are going to do something miraculous. Some, you know, it seems miraculous. I mean, if you flip coins enough times, you get a coin to stand on its edge. You know, it happens. Now, when that's the only one you got, the only coin you see, you say, wow, one flip, one coin on its edge. But you know that there's a whole bunch of the others, or the real, you know, 99.9999999999999% didn't do that miracle thing. But anyway, it seems a viable explanation for why there's redshift. There's redshift because space isn't a free ride, and the light is essentially tired. It's worn down a little bit by the process of having to navigate the real hydrogen atoms and the effect they have through scatter. Yeah, that's probably enough on that. So, that's probably enough on those subjects. I have a picture here of my other, the reason why thing. I know I have the reason here, and I just don't know why I can't say it. Alright, well, that's not on this page anyway. So anyway, next time, better explanation of that. So enough of a video, I think, and coming soon kind of thing. Like I said, the professor guy wants to spend more time preparing, and that's okay. You know, as long as I don't have to pay for that, and such. So hopefully soon, though, we'll be able to just discuss the fundamental, right, elemental elements of physics, and how rigorous the process was that led to what they now claim to be facts, like the existence of electric fields and magnetic fields and all of the other wave mechanics that they've accepted, when you don't need any of that stuff. Uh-oh, that doesn't look right for some reason. Anyway, till next time.